Hi everyone, welcome to the lecture on probabilistic learning in the machine learning lecture series by egate.ai. In the last lecture, we looked into logistic regression, a type of classifier. So before we get into other type of classifiers or a whole class of classifiers, let's first look into what do we mean by probabilistic learning. So there are essentially two different notions of probabilistic learning that we can see in the learning literature. One is learning probabilistic concepts, where we learn functions that produce a probability, or in other words, the learned concept itself produces a probability. So here, the learned concept is a function c which for a given input x provides a value between 0 and 1, which we can interpret as a probability. Now, an alternative way to look at it is called as Bayesian learning. So, rather than thinking about hypotheses that we will predict, the process of learning itself is probabilistic. The process of learning itself uses a probabilistic criterion to decide which classifiers are good. Here, the interesting part is that the hypothesis itself can be deterministic. It can be a Boolean function for all we know. So, eventually we will combine both of these settings, that is learning probabilistic concepts and Bayesian learning, where a probabilistic criterion is chosen to predict a probabilistic concept. We will come to that. Let's first look into Bayesian learning. Here, the goal is to find the best hypothesis from a set of hypotheses where the space of that hypothesis is called H, and using the observed data D. Let me clarify it once more. The goal is to find the best hypothesis H, represented by small h, from a space H of different hypotheses using the observed data D. So this is the same goal we always had. The main difference in Bayesian learning is that we define best equals most probable hypothesis in H. We need some way of characterizing a probability distribution over the hypothesis class H. We essentially need some way of saying how a particular probability is the most likely or has a particular probability as against either other hypothesis in the hypothesis space. So we need to know that which hypothesis has the highest likelihood, and we also in a way need to know that it is the best or the higher than others. A trivial way to know is to enumerate all of them, find a likelihood for each of them, and get the highest score, but that need not always happen. So it turns out we need to know something about the relation between data observed and the hypothesis. Here the hypothesis is plural, like all possible hypotheses. We have to capture relation between the data that is available to us as well as the various possible hypotheses in our space of hypotheses. So Bayesian methods have very interesting and useful roles. They provide practical learning algorithms. So while being elegant, which is always desirable, the issue is that just because something is elegant and if it doesn't perform well in the real world, it has limited utility. So a good thing with Bayesian methods is that it provides practical learning algorithms. Second thing is that it provides a means to combine prior knowledge with observed data. So we have observed data, which means that we know what has happened in the past or what has happened for similar instances of the input. And based on that, we have a way to estimate the likelihood for future events or future inputs or inputs that it has not seen but are similar to what it has seen previously. But what if we don't have the data, but by our experience or expertise, we know certain things are more feasible than others? Or I know that certain scenarios are more likely than others. Or maybe it's just something for my personal use and I have my own personal preferences, and is there a way I can encode those preferences without really having to demonstrate it via data or examples? So we have a means to combine prior knowledge with observed data that can help to guide the model towards something we know. Thirdly, it provides a conceptual framework. So I was talking about an elegancy of a method. So it definitely provide a conceptual framework, an elegant approach, which can very well be used for evaluating other learners as well. And finally, it provides tools for analyzing the learning process. Now, let's look at Bayes' theorem. I'm quite sure, or at least I assume at this moment, that we all are familiar with Bayes' theorem. So we may say that P of y given x is P of x given y times P of y by P of x. So forget about machine learning, it's just pure Bayes' theorem. So here x and y are random variables. These are nothing but random variables. So now we essentially need to predict the probability of the random variable y where we are given x. And in the RHS we can see that we have the term probability of y. We have the term probability of y. Now, this is saying that what is our prior belief on the outcome of random variable y without having the knowledge of x, or without observing x. And we call that as our prior probability. So remember in the last slide, we discussed about combining prior knowledge with observed data. And here we are talking about a prior probability, which essentially says what is our belief in y before we see x or before we observe x. So it is our belief that the random variable y takes a certain value before having encountered any evidence in the form x, evidence of the form x, sorry. Similarly, we have the likelihood term, which is nothing but P of x given y. Now, what is the likelihood of observing x for some value of y? So we want to find P of y given x, but here on the RHS, we are looking at P of X given Y. Now, based on the prior and the likelihood, we obtain the posterior probability. So what is the probability of Y given that X is already observed? Please do not confuse these terms. Likelihood means what is the likelihood of observing X given a specific Y. P of Y is nothing but the prior. And we basically want to know the posterior probability, that given that X has already occurred, what is the probability or likelihood of Y, and we are given the likelihood and prior. So posterior is always directly proportional to the likelihood and the prior. So if you see here the whole expression, there are two distributions over the random variable Y. And which are those distributions? It is the prior, and is it the likelihood? No, that is not dependent on Y, or it's not over the random variable Y. It's only conditioned on it. So the posterior is the second one. So we have to estimate P of Y, we have to estimate P of Y given X. Both of them are over the random variable Y. And Bayes' theorem states that these two are proportional to each other, dictated by the likelihood. So that's another way to look at it. Now please remember, in terms of learning, I have not said what is Y, what is X. So Y can be a hypothesis from our hypothesis space. It can very well be a label along with the data set. So we will get to that. Now, from Bayes learning, let's get back to, from Bayes theorem, let's get back to Bayesian learning after it's a machine learning class. So given a dataset D, we want to find the best hypothesis H. So given D, I want to find the best hypothesis H. And what does the best mean? So we define the term best using the posterior probability. All right. So best is nothing but the posterior probability of the hypothesis given the data. This is same as the conditional probability of a hypothesis given the data, and we define that as the best. So an important insight here are both H and D are events. So H and D are events. So D is an event. Among all the data sets that could exist in this particular data set is the one that came into existence. So let's see, if we have only one data set, how exactly we can call it as an event from a probabilistic sense. The explanation for that is that D is an event because there could have been different data sets. Let's say I take away one pair from here. That's now a new data set. Let's say I add in 5 or 6 data points. That's a new data set. Let's say I have a completely new set of data points and I'm discarding the old one and I'm only keeping the new one. That's also a new data set. So out of a lot of possible data sets, possibly infinite, this one has come into existence that we can use. This one as in the one denoted by D. So it is an event. Now what is H? H is the event that it is the true hypothesis. So if we have both of them to be events, we can simply apply Bayes rule here. So this is the same thing we have seen previously, but now in terms of a hypothesis and data set. So it is probability of h given d is nothing but the expression probability of d given h times p of h by p of d. So here p of h is the prior, it encodes background knowledge. So in the absence of any data, do we have any expectation of the hypothesis? It can be any form of information, it can be a preference. So when we know nothing about the hypothesis, if we think that all possible h's, all possible hypotheses in the space of hypothesis are equally possible, or for example, in the absence of any information, we may simply say it's a uniform distribution, that every hypothesis is equally likely. Similarly, likelihood asks, what is the probability that this data point is observed, given that the hypothesis is H? So for every data point in D, we can say, if I am using this particular hypothesis, because let's say I have m possible hypotheses in my hypothesis space, if I am using a particular one, what is the probability of each data point in that data set? Again, we can compute the likelihood for each data point, or we may compute it for the data set as a whole. So the crux is that, yes, what is the probability or likelihood of the data set, or what is observed given a particular hypothesis? That validates whether a hypothesis can hold good or can predict well in the future events. And there is this denominator PD. It essentially asks, what is the probability that the data D is observed? So it is independent of any knowledge about the hypothesis. Without the hypothesis, PD is going to be just telling what is the possibility that this particular data set can be observed in the real world. So we are essentially interested in identifying H or learning something based on H, hypothesis H. The denominator is independent of H. So it can very well be treated as a constant. We are concerned only with finding the best hypothesis H. So let me reiterate that. If I have a hypothesis H, it's a capital H, where I have, say, K such hypothesis. For each hypothesis, I can compute it using this Bayesian learning approach. But we are interested only in the best one. There is no necessity that we have to compute it for everything, for each H. What I am interested, or what we are interested, is only for the best hypothesis. So we are interested in maximizing the H. So we may very well treat this P of D as a constant because it is not dependent on the H. So now let's see how we choose a hypothesis. Maximum a posteriori criterion, or MAP as we simply say it. It finds the hypothesis H map that maximizes the posterior probability of the hypothesis given data. So we are doing an argmax, implying for every hypothesis in the hypothesis space H, we are trying to maximize P of H given T, which is a posterior probability of the hypothesis given the data. Now using this expression, we know that P of H given D can be written as P of D given H, P of H, P of D. And as I have mentioned, this is a constant. So I am ignoring it because in maximizing P of H, the constant doesn't affect the outcome. So I will write it as P of D given H, P of H. So we already know that the posterior can be written as in terms of the prior and likelihood. We have seen this. We also know that the denominator does not depend on h. So since we are interested in is finding a way to maximize h given d, we can treat the denominator as a constant and we ignore it, and we are finally arrive at this expression. Sorry. So given some data, we find the most probable hypothesis by maximizing the posterior of the hypothesis given the data. It is directly proportional to the prior or our preferences in the hypothesis space. However, if we have no such preferences, or if we don't know, or if we don't have any such information, then it is equivalent to saying that the prior is a uniform distribution. Let's say it is uniform. If that's the case, then so for a data set, irrespective of the hypothesis, the prior will be of same value, or in other words, a constant. So it can also be pulled out of the argmax, and that leaves us only with the likelihood term. So we started off with the posterior, we ignored this p of d because it is not dependent on h, and that's how we compute the maximum a posteriori. Now I'm talking about a special case in MAP where I'm saying that I don't have any preferences or I don't have any prior information. So I am assuming that all hypotheses are equally likely, or in other words, I am giving a uniform distribution. If so, then this also becomes a constant. I ignore it. If it's constant, I ignore it because it's not affecting the argmax. So I end up only having to focus on the likelihood term. And under this special case where the prior is a uniform, prior is ignored, or prior is a uniform distribution, we say that it is the maximum likelihood estimation or maximum likelihood hypothesis. Thanks for today's lecture. So in the next lecture, we will look into what is generative and discriminative classifiers. What are those? And then we will go into like where exactly does logistic regression fit, and we will look into naive Bayes, which is the other form. So if logistic regression is discriminative, then naive Bayes is generative. If naive Bayes is generative, logistic regression is discriminative. Only thing is that you have to wait till we get there. Thank you.